future generation, you need one of the aspects is to improve the performance, the whole performance, okay, of this system. Okay, so the first method here we have, the simplest one is called diversity, okay? And the diversity is something very logic. So here, as we can see here, the main goal for diversity is to combat the effect of fading or improve the error, right? Because typically fading will affect the signal, will degrade the signal, and it will produce more errors at the receiver side when you try to detect this faded signal. So I need here to do some tricks in order to improve or improve the error or mitigate the fading, okay? So due to the signal propagation and fading channels. Diversity technique or techniques are used to reduce the chance that the received signal experience a deep fade. The basic idea is to send same signal over independent channels, okay? So suppose that, like, logically, if you have very important information and you need to tell someone this important information, this someone not at the front of you, okay? You need to send him this important information. Remember, the professor changed the time of final exam, right? So naturally, you will repeat your information to your friend, or you send the same information to your friend multiple times to ensure that at least he will get the right information. So you might call him if he didn't reply. You might call your friend and tell him, please tell that person the professor changed the final exam time, right? And you will call another one to make sure, like, you will repeat trying to deliver the same information from the source to the destination in order to make sure that this information is delivered correct, right? This is natural thing. And this is what we are doing here in diversity. The concept of diversity, you send the same symbol, the same signal, okay? And the keyword is the same signal, okay? Because if you send multiple signals, different signals, okay, so this means that I don't care, right? I am focused on a certain part of information, or at least one information, right? So diversity means you need to repeat or send the same signal over independent channels. And the second important keyword here is independent channels. Because if you send the same information over the same channel, so it will experience the same noise, right? So there is no need actually to repeat the same information over the same channel. For example, if you, the same example as I mentioned, like you need to deliver important information to your friend, all you need is to deliver multiple versions of the same information, but using different persons. But if you repeat the same information to someone, like you call your friend and he didn't answer, and then you call another friend and you told him, please tell that person that professor changed the exam time. And even if you repeat it to that person like 100 times, there is no need actually to repeat, right? Because actually, if he forgot, this person you just called, if he forgot, if he died, if he whatever, he like became busy or something like that, he will not deliver the information. But if you call one friend, another friend, 3 friends, 4 friends, if someone has any problem in delivering the information, you make sure that the other one will deliver the information, okay? So the key idea is to send the same information over independent channels. Independent means the behavior or the noise or the fading in each channel will be different. Because if each channel will experience the same behavior, the same error, the same fading, actually there is no need, there is no meaning for repeating this information, okay? So This is actually the general concept of diversity. So diversity, I repeat the same signal over independent channel. Okay? And we will see the types of diversity. How can we achieve this kind of independent channels? What is the type of diversity? By the way, there is a lot of diversity categories, but we will focus in what is called micro diversity or just diversity. Okay, but like if you open a book or like communication books, you will find a lot of diversity techniques. But we will focus only on 5 major categories, as we will see now. Okay, so the idea is simple but powerful. Okay, if one signal copy is fading deep, is in fading like deep fade, so there is another chance is that other copies aren't. Okay, so combining them will improve the overall reliability or the reducing the error. And we can have actually an example here. Okay, so this example, let's solve this example here. Let's to understand the concept of the diversity or repeating the signal multiple times. Okay, suppose that I sent, this is what I wrote here. Okay, so suppose that the original symbol I sent at the transmitter side, I sent a symbol of 1 1 1, 3 bits. You sent them, you didn't repeat, right? This is just a symbol. Okay, you send a symbol of 1 1 1, and due to the noise you repeat this symbol. Let's say you need to do diversity or a repetition, right? Similar to repetition code, okay? So you send this symbol 3 times. So you send this one here, maybe using a channel 1 here, channel 1, and due to the noise you might receive it error in the second bit, okay? So this one is error bit, because you know the original one, it's supposed to be 1, okay? And you send through another channel 2, because it's independent, so the symbol here, or the transmitted symbol, will experience to a different error, or a different fading, a different noise. So I might receive error instead of in the second bit, I might receive it in the first bit, okay? So instead of receiving 1 1 1 1, I receive 0 1 1, okay? And the same thing if you have another third channel, and due to the error different than the first channel, second channel, because the third channel is independent, which means that the statistical behavior or the noise will be different than the first 2. So you might receive the error in the third bit, okay? So you might receive, instead of 1 1 1, you might receive 1 1 0, okay? So as the receiver side, none of these symbols is the correct sequence, right? So if I have only one channel, instead of receiving 1 1 1, I will receive 1 0 1. So I will have one error here. If I have only one channel, I will receive 0 1 1. Okay, I might receive 1 1 1, right? It's okay. But like, suppose that this is the worst case, for example. So at the receiver side, because of this kind of repetition, you can take these 3 versions and try to find the correct version out of these 3 versions. So you might take this one as like 1 0 1. This is from a channel 1, and you might have from a channel 2, you might have 0 1 1, and from a channel 3, you might have 1 1 0. And with the simple formulation of like majority vote, you can look at the first bit. What is the majority vote here? Is 1, right? So because I have 3 copies for the first bit, okay? 2 of them saying it's 1, and 1 of them saying it's 0. So majority vote will be 1. And the same thing here, the majority vote is 1, the majority vote for the third bit is 1. So with these 3 copies, with this even we have errors, you might receive the correct one, okay? However, if you have only one channel, without this kind of repetition, without this kind of diversity, I might have only like this one, and I might detect it wrongly, okay? So with this kind of, as you can see here, you repeat the same signal, and the keyword, the two keywords here, you repeated the signal, okay? Because if this one is different than that one, so nothing I can do here, okay? So I know that these three versions follow one symbol only, so you repeat it. And also the second keyword is you have independent channels, because for example, if you send the same symbol over the same channel, you will obtain the same error, right? So you will obtain 101. And even you send here 100 times, you receive 101. If you have majority vote, the majority vote will say 101, right? So you need to change the environment, which means that you send it over an independent channel in order to obtain a different error. And this different environment will help you to try to find the correct one, okay? So this is what I mentioned here. Consider that you transmit 111 and you receive like 3 copies here, and this is the 3 copies you got, and none of them is correct, and all together, after you combine all together, you will obtain the correct symbol out of the majority vote, okay? So this is actually the basic concept of diversity. Repeat over independent channels. Okay, but how can I achieve that?
Sorry, quick question.
Yeah.
What if you have 3 channels and when you compare the bits of each and you end up with a error signal, I guess. Let's say the first channel is 100, and you do the bitwise comparison.
100, right?
Yeah.
Yeah.
And
you
the
have
rest-
2 errors right here. The original one was 111. Okay. What
Yeah.
else?
And the rest you keep it the same.
Okay. Like tell me what's the
011
011, right?
and 110, I guess.
110, right?
Yeah.
Okay, you do majority vote, and you might have error, but this error better than the first one, right? For sure, like on average. So you take majority vote here is 1, majority vote here is 1, majority vote here is 0.
Mhm.
So you have 2 bits correctly and 1 0, right?
Yeah.
So of course, diversity cannot eliminate, because I say mitigate, right? Reduce the error, not eliminate completely, right? So better than actually, and if you try, for example, if you try to improve the performance, you might have, instead of 3, you might have 10, for example, 10 versions, and so on. Like it's a trade-off between the complexity, the spectrum as well, and the number of errors you can mitigate, okay? And again, this is just a simple example, right? So let's see here the types of diversity, okay? Because not all the diversity like that. This is just a basic example about why the repetition might improve the performance, okay?
Okay. So if you want to improve the performance, do you just increase number of channels?
If you need to improve the performance, you need to what?
Increase the number of channels?
Yes, yes.
Okay.
Independent channels.
Yeah, that's right.
But you sacrifice a spectrum, right? So because, for example, instead of you sending multiple signals to improve the spectral efficiency, to send more information, you sacrifice this more information with like accurate information. Depends on the application, right? So it's a trade-off between how many, according to the requirements you need in your system, okay? So, okay, so let's continue. Okay, so we have 3 types or 5 types of diversity here for small scale fading, which is in some books like they call them micro diversity. So we have a spatial diversity, like some books, other books name it space diversity. We will know why. A spatial or a space diversity, temporal diversity or time diversity, frequency diversity, angular diversity, polarization diversity. Okay, so let's start with a spatial diversity, which is the most common one in modern digital communication. So for spatial diversity, I need actually, this is one of the most effective and widely used techniques to compare a small scale fading in wireless communication, okay? And it's used for current or modern technologies like LTE, 5G satellite, or even Wi-Fi. Okay, so we use actually multiple antennas, and each of these antennas are placed in a different space, like there is a space between each of these antennas. That's why it's called a spatial diversity, because I need to send multiple versions. But how to send these multiple versions in wireless communication? We have like 5 types or 5 ideas to send these multiple versions of the same symbol. Okay, so I can actually, you know that in wireless communication, after you modulate the signal and you're doing all the stuff in the transmitter, you have antenna, right? And you transmit your antenna, you transmit your information using this antenna, and this antenna radiates everywhere if it's omnidirectional antenna or it's directive antenna, according to the type, whatever, okay? So you transmit your information with that antenna. So you can actually send another copy from different antenna, right? So you can take the same information, send it through this antenna, and make a space between this antenna and the second one, and you send the same information, right? So you make the separation between these antennas. That's why it's called a space diversity. You do diversity means you repeat the signal or send multiple signal over a space or over a spatial, right? So you send here, actually you can send or you can receive, right? So you can send from one antenna and you can receive from multiple antennas. So this idea will raise another subcategories of spatial diversity, which is, for example, you need like the type of spatial diversity. You might actually have multiple antennas at the receiver side, okay? So, for example, someone is sending information here. I can have my antenna, I can stay here, or I can like leave a space and receive the information here. I can leave another space, receive the same information here. I am the receiver side. So you can have multiple received antenna at the receiver side. And this type is called SIMO, right? So single input, multiple out. I will add it here. Or actually, from the transmitter side, you can transmit the same information from different transmit antennas, right? And you receive it using one antenna. This type is called MISO, right? So it's multiple input, single out. Or you can do both. You can have multiple antennas at the transmitter side and multiple antennas at the receiver side, which is MIMO, which is a popular one till now. With like, if you open any paper in wireless communication, you will see MIMO, right? So MIMO means that I have multiple antennas at the transmitter side, I have multiple antennas at the receiver side. And you can actually, you can send more than not only one antenna, not only one information. You can have like subcategories of it. But like we are focusing on diversity. Okay, so you have SIMO, you have MISO, you have MIMO. Okay, for without any kind of diversity, you have SISO. You have single antenna, single input, single output. Okay, so this is actually the graph for it. So this is a natural communication system. I have only one antenna at the transmitter side. I have one antenna as a receiver side. Or you can actually have multiple antennas as the receiver side. This is multiple output, okay? And I have only one antenna at the transmitter side. So I send one information here, but I received it multiple versions. Okay? Or you can send the same information many times using multiple transmit antenna and receive it only once. Or you can do both. You can have multiple antennas at the transmitter side and multiple antennas at the receiver side. But remember, I'm repeating the information here. However, I need to make sure that each channel must be independent. The condition here to have independent channel, right, is to make the separation between these two antennas greater than the half of the wavelength. And actually, this distance or this ratio varies based on the system. Okay, some systems require 10 of the wavelengths, like 10 times of the wavelengths, because according to the nature of the environment itself. If it's empty space, or if we have a lot of objects inside this environment, so depends on the environment or the channel. I can use the separation, right? But it's greater than, at least greater than the half of the wavelengths, okay? But just because you might read in a different book that according to the information, they put it like 10 of the wavelengths, 5 of the wavelengths, double of the wavelengths, again, depends on the environment. But what I need to know is the separation is based on the wavelengths, the signal wavelengths, right? So it's not based on, I cannot say that I will put this antenna here and that antenna here, and by my naked eyes, I can say that this antenna, like this separation is good. No, it depends on the operating frequency you are working on, right? So this is to make sure that these antennas will experience different channel environment, which can be called as independent channels. Okay, independent means that I don't care about the adjacent channel, I'm independent, okay? Okay, so the limitation of using this spatial or space diversity is it requires actually additional hardware, because as you can see here, instead of having one RF chain, this one from here, from the transmitter to the receiver, this is called RF chain, okay? Like radio frequency RF, radio frequency chain, right? So this chain typically in practice is very costly, okay? It's not like you say no, it's very costly because, yeah. So anyhow, like one of the limitations of this spatial diversity is that first of all, you need a space, right? I'm saying that it's called the space diversity. You leave a space, you set up your second antenna, you leave another space, you set up another antenna. So like, if you have, for example, very limited area device, similar to like a smartwatch or whatever, so you have a very tiny space, so this number of antennas might be very limited, okay? So this is the first requirement. The second, or the first limitation. The second limitation is it requires additional hardware like antenna and RF chain, because as I mentioned here, as your friend asked me, like if you need to improve the performance or reduce the error, you need to increase the repetition, right? So in this case, I will increase the number of antennas. And in this case, first of all, the antenna is additional implementation cost, okay? And the second thing is, as we will see in what is called the combining, because you have multiple versions, you will have extra cost in signal processing. And another cost is the RF chain. Here we have, for the traditional system, which is SISO, we have one RF chain, but here we have two RF chains. If I have MIMO, I have multiple RF chains, which is will increase the implementation cost of the system. Okay, so nothing is like good forever, so anything has some kind of limitation. Okay. However, with this kind of limitations, we still using this type widely nowadays in modern communication. However, the rest of types still we are using them, but not widely like that. Okay. So after you send this information or multiple versions of this signal, so you need to deal with this signal at the receiver side. Okay, so you have multiple versions, similar to what I wrote on the board now. You have multiple versions, and these multiple versions you need to deal with. Okay, so typically we use what is called the combination techniques. Combination means that I have multiple versions, I have multiple signals, and I need to combine them in one signal, right? Because at the end of the day, I know that it's only one signal. But how can we select the information based on what I have? Okay, so 3 ideas raise in your mind. The first idea is, let's select the best quality signal, right? Which is called selection combining. Okay, so I have multiple versions, and I need to estimate the signal strength of it, or the signal to noise ratio, because the signal to noise ratio is one of the factors we consider in wireless communication. So you can select the best signal. Okay, so suppose that I have, don't have pen now. So suppose that I have like 2 signals, one with signal to noise ratio is 5 dB, and another signal, the same version, but with like the same signal, but another version, or the same version but another signal. Okay, so I have the first version is 5 dB, and I have another version with 10 dB. Which one you will select? 10 dB, right? Because 10 dB is like is healthy or healthier than the first one. Okay, so this is a concept of selecting combining. Most of these techniques, guys, are very logical, right? So again, I have multiple versions. How to deal with them? I have 3 versions, 4 versions, 5, whatever. One of the ideas selects the best, okay? Which is selection combining. Choose the antenna with the highest signal to noise ratio, okay? It's very simple, but it's not optimal, okay? Why? Because I didn't invest the rest of the signals. Remember the example I just mentioned before I start explaining these types? With the 3 versions, even the included noise, I successfully obtained the original symbol, right? So for signal, for like selection combining, I don't care about the rest of the versions. I just select the best one, which is very simple, but it's not optimal. The second one here, which is the most commonly used, is called maximum ratio combining. Okay, so for maximum ratio combining, you make a combination between all received signals and like multiply each signal by a certain weight. Okay, so for example, when you have 3 signals, the best signal you multiply, you give it a very high weight. Okay, however, you will take also in your consideration the rest of weak signals, but you give them a smaller weight. Okay, so and then you combine them together, like add them together, and actually for all these 3 types, or even like there is a circuits and like block diagram, but like again, we will not focus on that because I do believe that you discuss this in more details in wireless communication course if you took it. So here we will not focus on the circuit building, but here actually for each symbol or for each signal, I give each of them a certain weight, and this weight depends on the signal to noise ratio. If the signal to noise ratio is high, this means that this signal is very good. So I cannot add this very good signal to another weak signal, Okay, so I will consider the weak signal, but I give it a smaller weight. I will take the higher signal, the strong signal, but I will give it a strong weight, which is makes sense. Okay, that's why here I maximize. This is called maximal ratio combining, which is like very. This is the best type here in this kind of combination. Okay, so as you can see here, this is the best performance, but it needs like a lot of operations in order to estimate the signal to noise ratio for each of them, and then multiply and make weights for each signal. And like in some problems, they do or solve optimization problems to find the maximum ratio combining. And the third type is similar to actually maximum ratio combining. I will consider the whole sequence, the whole versions, but I will give them equal weight. Okay, so I will take the strong signal and I will consider also the weak signal, both of them equal weight. Okay, this is called equal combining gain. Okay, so equal combining gain is pretty similar to maximum ratio combining, but here we have fixed weight for all signals. However, for maximum ratio combining, we have a variable weight or a variable weights based on the signal strength itself. Okay, but these two types, number 2 and 3, maximum ratio combining, MRC and AGC, are using the whole sequence. Okay, however, the first type is selecting only the best one. Okay, so regarding the simplicity, regarding if we can, I might ask you, for example, rank them according to the perspective of simplicity or complexity. So the first one, the best one, the very simple one, simpler one is the first one. Okay, I just select one signal and that's it. I don't care about the rest of the signals. I will not combine, I will not add. I just select the strongest and that's it. Okay. The second simpler one is equal gain. Okay, I add all the signals together without doing any kind of signal to noise ratio estimation. Okay, so I will consider how can you know that if you have 3 signals. Okay, if you have 3 signals. If you don't understand, just let me know. So if I have 3 signals, for example, and I have the first one is the strongest one, how can you know that this one is the strongest one? You need to estimate the signal to noise ratio, right? So to estimate the signal to noise ratio, we need extra information or extra processing. This is what we are doing here in maximum ratio combining. But actually for equal gain, I took the whole 3 signals and add them together and that's it. I don't care which one is a strongest one because I don't need actually to estimate the signal to noise ratio. So regarding the simplicity, the third type is simpler than the second type, but is complex, more complex than the first type. Okay? But regarding the performance, look at the performance. Which one is the best? The best is maximum ratio combining because you are taking the whole signals together, but you look at the weight of each one. If you have a signal with a strong signal, you give it more weight. If you have a weak signal, you take it into your consideration, but you use a smaller weight. Okay, so you have here the maximum performance, and the second maximum performance, or the second one is equal gain, which is considering all signals, is better than considering only one signal, right? So this is the arrangement, but you need to look at the different perspectives. Okay, so this is the first type, which is the space diversity. Okay.
For the previous slide,
Yeah.
first one, how can you know the highest one if you don't evaluate the SNR of all antenna?
You estimate, like you have like 3 channels, right? You have 3 channels. You estimate the signal to noise ratio for the first channel. You estimate the second rate. Like practically, how to do this? You send pilots.
No, I mean like for the first one, you say it's simple, but you need to evaluate the SNR for all of them to know the highest one.
Yeah.
So I think the complexity is the same as the second one.
No, but like after you estimate signal to noise ratio, what you will do? You select the best, right? But here, after you estimate the signal to noise ratio, what you will do? First of all, you multiply with each signal and then you combine them. You have extra processing. You know what I mean? Okay, so but here, it just, if you look at the circuit here, if you open box and you look at the circuit, you will find it's just a switch. And this switch is controlled by the best signal, right? So like if I have like 4 signals here, like you select the best one. But here, you have, after that you have like addition, multiplication, you have another circuit in order to make this combination, right? Okay, so like, I think if I wrote the formula, it might be more clearer, right? But like anyway, yeah.
So the complexity of the first one and the third one is equal, right?
No, not an equal, right? Because typically here, I know what you mean, right? Because here I estimate signal to noise ratio, however I don't here, right? But typically for signal to noise ratio, you estimate it once, right? I know that you are a research student, right? So if you do a simulation, did you change the variance of the noise over time, or you consider it's like fixed at like over a certain period of time, right? So you have actually signal to noise ratio is you can estimate it once, and you know that this channel is always good for this certain period of time. So not only every second you estimate signal to noise ratio, right? You estimate it once, but here for equal gain, you add the symbols together every second, every millisecond, every frame. You know what I mean? Yeah. You got it? Yeah, okay. Okay, so the second type is a temporal diversity or time diversity. Instead of sending multiple versions of the signal over space, you can send it over time. You can send it now, you wait a little bit, you send the same symbol, after a certain time, you wait and you send, right? Logic, right? So you can, this is called time diversity. So time diversity, we transmit the same information at different times. But again, the receiver increases the likelihood of correctly decoding the message, or we know all that. Since fading is typically time varying, okay? So typically we have the fading is time varying, and I know that if I wait it a little bit, the time varying may be changing, okay? So in this case, the symbol might experience different errors than now. But the condition is, you need to transmit the same symbol, you repeat here, but we need to transmit over independent time slots, right? How can we know that this is independent time, independent time, right? So we discussed last time what is called coherence time. What is coherence time? The statistical behavior, the period that statistical behavior can be considered as a constant, right? So you can actually send one symbol over a certain coherence time and wait for this coherence time to be done, and then you send another symbol, because you know that after this coherence time, the channel will experience a different statistical behavior, right? But if you send the same symbol multiple times over the same coherence time of the channel, in this case, according to the definition of coherence time, the statistical behavior is almost constant, right? So in this case, the noise, the error, the fading will be the same. So logically, you need to wait until the environment or the statistical behavior will be changing, and then you send another symbol, right? So this is the condition here. So we have two conditions now. For space diversity, we need to space the antennas greater than the half of the wavelengths, right? The condition here for time diversity is you need to send the symbol with a greater, you wait a period of time that greater than the coherence bandwidth. I'm sorry, the coherence time. Okay? So, and again, after you receive the signal, you might need to do the same combination techniques as we did before. You might use equal gain, you might use maximum ratio combining, or even selection combining. The limitation here is increased because we are speaking about time. Okay, first of all, I will increase the transmission delay. Imagine that you need to send one symbol, like you repeat it 3 times. I send, I wait. I send the same symbol, I wait. I send the same symbol, I wait. However, in the first time, you send the whole sequence or the repeated versions at the same time, simultaneously, okay? But here I need to wait, which means that I will increase the transmission delay, okay? And actually, which lead us to this type of diversity is not suitable actually for live broadcasting or real-time application, which means that like interaction. For example, suppose that you are watching your favorite sport, like a live game, and suppose that each symbol is repeated like a few times, okay? So you might watching the first minute of the game and the game is already ended, right? So typically it's not suitable for a practical applications that require that require like a time constraint, or the time is very important on this type of application, like a voice, right? So video conference, whatever, okay? It reduces the effective data rate, because the data rate, how many bits you send, or useful bits you send over a certain period of time, right? So like, suppose that I have a system that transmits 3 bits over per second, okay? So, but I might use the 3 bits for 3 users or for different information. However, in this time diversity, I might use the 3 bits, the same 3 bits for single information. In this case, even I send over 3 bits, but the effective data rate will be 1 bit only, right? Because I repeated the symbol 3 times, okay? So typically you reduce the effective data rate. It's not data rate, right? Because the data rate will be the same, number of bits per second, but the effective one, okay? Because I sent the symbols 3 times, but originally it was 1 symbol, right? So the effective data rate now, effective data rate will be reduced, okay? And also, at the receiver side, you need a memory. Why the memory? You need a memory because you will not receive the symbol or the versions at the same time. You receive and you'll wait. So what about the current received signal you just received? You need to store it, right? Otherwise it will be gone. So, and you receive the second symbol or the second version and you wait. You need to store it. So I need actually to prepare the receiver to have memory in order to store this kind of versions, okay, which will increase the buffer time, the buffer size, and also the computational complexity or the complexity implementation cost of this type of systems, okay? But I don't need this memory in the first time or the special diversity. Okay, so instead of using space to send the diversity, instead of using time, I can use the frequency. Okay, so I can send the same information, but with different frequency subcarriers, right? So in this case, I can name it as a frequency diversity. So in frequency diversity, I send multiple versions over a different subcarriers or frequency carrier, okay? So, and the condition now here is to make sure that these subcarriers are independent, okay? How can we say that these subcarriers are independent? We need to wait after or use this subcarrier separation between these subcarriers greater than the coherence bandwidth. According to the coherence bandwidth we defined last lecture, the frequency range that the statistical behavior of the channel will be the same or flat, okay? So if you use multiple subcarriers within this coherence bandwidth, all of them will experience the same behavior, which will not help us here, okay? So you need to make the separation between this subcarrier and the another subcarrier. The separation will be the coherence bandwidth, okay? So this is the condition here for a frequency diversity, but it's the same concept. You send multiple information and that's it. Suppose that this is just illustrative example here. I have, this is a frequency 1, frequency 2, frequency 3. Suppose that I have a strong one here and weak signals here, okay? So I might use this one to detect the symbol instead of these two weak signals, okay? And this separation between the first subcarrier and second subcarrier, it must be greater than or equal the coherence bandwidth. Okay, so, and actually this type is also commonly used, especially the concept actually of this frequency diversity can be applied using OFDM. Okay, if you are working in wireless communication field in research maybe, so you are familiar with what is called orthogonal frequency division multiplexing. So the whole frequency, I divided it into orthogonal frequencies. Okay, so the whole bandwidth, I divided it to small sub bandwidths, which will be orthogonal, and there is it's like there is a box there in just to explain OFDM, right? So how to choose the separation and what is called cyclic perfects, whatever. But anyhow, the concept of OFDM is to use a small sub frequencies, and these frequencies are orthogonal. That's why it's called orthogonal frequency division, because you divided multiplexing. Okay, so, and this is still currently used now in 4th and 5th generation. Okay, by the way, guys, you might experience like combination between two of these techniques in practice. Like for example, in modern wireless communication, you might find MIMO with OFDM. Okay, so MIMO is a spatial, right, or a space diversity, and the OFDM is a frequency diversity. So you might combine between like two types or more, right? So yeah, but anyhow, we will not speak about that, but if you are reading or whatever. So limitation of this type require more bandwidth, like compared to the time, I wait the time, I increase the delay, but here I need more bandwidth, and I told you before that the bandwidth is very expensive, okay? So I need more bandwidth here. And also it's very complex in equalization at the receiver side, because with each subcarrier you need to have a big circuit, okay? So you need to have what is called a feedback loop, PLL, you need to also like to look at a certain frequency, you need a lot of circuits actually to detect only one carrier. Okay, what about if I have multiple carriers? This will increase the complexity of the network like dramatically. Okay, so this is the third type. So the last two types, angular and polarization diversity, this is not commonly used, but you can find some applications about that. It follows the same concept. Angular means that angle, right? So I can send multiple information using different angles, right? So I have here, this is the base station and this is the receiver side. I have only one antenna, but I can send the information. Remember, in the basic course of wireless or digital communication, you have FM, PM, right? You have frequency modulation, you have phase modulation, right? So you can actually send the same information using the phase, right? So in this case, you can use antenna, and you can actually, with this angle of arrival of this antenna, you can receive a different information with angle of arrival. Okay, in this case, you just created multiple versions of the signal. Okay, the limitation requires a complex antenna structure, because you are dealing with antenna now and you are playing with the angle of arrival, and in this case you need to have more complex antenna structure. and also you need more signal processing. Like typically, if you are working in antenna fields, it reflects on increasing the signal. You have a question? Is the signal processing? You have a question? Okay. So for example here, you might send or you might receive the signal with angle of arrival of 30. You might receive another version at 60. You might receive another one at 110, whatever, right? Here for polarization diversity, instead of receiving the signal in multiple angle of arrivals as the previous type, I can actually send the signal multiple times, but using a vertical and horizontal, okay? So the angle between these two beams or these two signals will be 90 degrees, okay? So I can send it vertical polarization or horizontal polarization, okay? And this kind of modes you can control in like electromagnetic wave. If you studied electromagnetic wave, you can see that there is some kind of modes that there is angle between or the polarization angle between these modes together, okay? And again, all of these types, guys, I can use combination techniques, which is like selection, combining, maximum ratio combining, or equal gain as a receiver side. The limitation for it, if the transmitter and receiver antenna are not aligned properly, okay? So again, you need to have alignment or synchronization between the transmitter and receiver because you are playing with angle, okay? So like, for example, like angle means that this is a horizontal one. If your antenna at the receiver side was like polarized with a certain angle, in this case, you will have what is called a mismatch between the transmitter and receiver, okay? So you need actually to keep trying to align this transmitter and receiver, which is very difficult with moving objects, right? Like, how can I align this antenna of the mobile, moving a mobile? It's very difficult, right? So it might be suitable for certain number of applications, okay? Require dual polarization antenna, okay? So this is a type of antennas that like you need to consider dual polarization antenna or dual polarized antennas in order to separate between the vertical vertical polarization and the horizontal polarization, which will increase the system cost. Okay, so this is the types of diversity I can use, and all of them will try to improve the error, right? Will try to reduce the effect of fading, okay? Because the fading will reduce the reliability of the signal, which will increase the error. However, using this kind of diversity, I can actually try to reduce the effect of this fading. There is another type of mitigating the fading, which is called a channel equalization, okay? So you can do equalization at the receiver side, okay? So the difference between equalization, as we will explain here, I'm designing equalizer at the receiver side. But for diversity, I'm using some techniques, like I repeat the signal, right? How to repeat the signal? I can set up some antennas, like at the transmitter side even, right? Even you receive the signal multiple times, but for equalization, you have a certain block that can equalize or compensate the error itself physically, okay? So this is the second type of fading mitigation, which is equalization, right? So you might not find this type in the paper, okay? So you need to speak to include this, because the question in the third assignment is to make a connection, not only summarize the paper, but also make a connection between what you have read and what you studied here. So this equalization is not in the paper, okay? But you need actually to speak about it in the third assignment, okay? Okay, to make a connection between the paper and the lectures. Okay, so in a channel equalization, we we are doing some kind of compensation, okay? So the aim is to recover the original transmitted signal by compensating the effect of a channel, okay? So I consider the channel as the transfer function, like a block, right? And I need to inversely affect this channel in order to improve or reconstruct the original signal, okay? So the type of equalization, this is, for example, this is the received signal in vector form. So I have the received signal here, and I have the channel multiplied by some transmitted signal plus the noise, okay? So this transmitted signal, this channel is really fading a channel or fading a channel. Okay, so with this received signal, I just received this signal, and I need actually to equalize this signal, okay? So I have, to be honest, I have more than 15 types or even more of equalization or equalizers. I just like mention a few of them, okay? But you know that there is types of equalization. So linear equalizer or non-linear equalizers, okay? For linear equalizer, what we will be studying now, or this course, we will be studying what is called the zero forcing equalizer, minimum least square error equalizer, which is a type of linear equalizer. And one of the non-linear equalizers is called maximum likelihood equalizer, okay? Which is the most common one, or the most optimal one in wireless communication, maximum likelihood equalizer. And we have what is called rack receiver. We will not speak, we just speak about it, but we will not include it in the exam for sure, okay? But this is the common or the wide types of equalizers. You might see adaptive equalizer, you might see decision feedback equalizer, you might see a lot of different equalizers, but again, we will not be able to discuss all types of equalizers. Okay, so let's talk about linear equalizers, which we have here two types, like two subcategories out of linear equalizer. Okay, so linear equalizer means that I apply linear filter, just linear filter, because again, I deal with a channel here. We are treating the channel as a black box, right, or a block diagram with a transfer function, okay? So here, for example, like linear equalizer, I just have H here, I just inverse H, and that's it. This is the type of linear equalizer. I treat the received signal as linearly inversely proportional with the channel gain here, because this is a channel gain. All I need, because the problem here in this H, which is the fading itself. So for linear equalizer, I just cancel it, which means that I divide this received signal by H, okay? So this is a linear equalizer. But like we have two major types here of this equalizer, linear equalizer. We have zero forcing equalizer. So for zero forcing equalizer, it inverts the effect of the channel, it invert, right? By applying inverse filter, okay? It's just the inverse of the channel matrix. Effectively forcing the intersymbol interference to be zero. Like ideally, if we don't have noise here, if we have the received signal only, H, X, and X here is the transmitted symbol, and H is the fading channel. So typically, if you divide this equation by H, you will get X, right? So this is ideally. It's similar to you are forcing the interference to be zero, okay? So ideally, this zero forcing, it came from the name of you are forcing the interference, intersymbol interference to be zero, ideally. But unfortunately, this is not true, right? So typically, if I have the received signal like that, I use the weight of the filter or the transfer function of the filter to be the inverse of a channel. Actually, this is the pseudo inverse, right? So you're supposed to be familiar with linear algebra. For example, if you have channel matrix H, and this channel is a square one, right? So it's like 3 by 3, 4 by 4. Then you can obtain the inverse of it, right? But if you have rectangular form like 4 by 3, channel matrix is not a square. In this case, how you can find the inverse of it? You find what is called a pseudo inverse. Okay, so this is called a pseudo inverse, right? Like pseudo inverse, right? So, or fake inverse. Pseudo in English means that fake inverse. Okay, because you cannot find the inverse of rectangular one. Okay, so you just find the pseudo inverse. There is a proof for that because like. Yeah, but anyway, we will not talk about proof. Okay, so here I find the pseudo inverse. This rule actually will be only each the inverse of this channel if we have a square matrix. Okay, so if each here is a square matrix, this one, this rule, this weight will be H inverse directly. But since we have like the general rule, because in wireless communication or digital communication, typically we don't have a square matrix, okay? Because the square matrix means that the number of transmit antenna equals the number of received antenna. But ideally, we have like the number of received antenna is higher than the number of transmit antenna, okay? So in this case, we usually have rectangular matrix, not a square one, so we use inverse one. But anyhow, it's inverse of the matrix. So what we will do, once I receive the signal, I just multiply it by the filter, right? Linear filter here. This is a zero forcing. W, the weights of zero forcing. So if you multiply this one here, you will cancel, this one will cancel this one here. So you will obtain X multiplied by this noise. You multiplied by this noise, okay? So as you can see here, this is the inverse of matrix, right? So the inverse of matrix or the channel matrix, suppose that typically if you are in practice, the matrix itself is a smaller values, right? Very small values. And if you try to find the inverse of it, you will, as you can see here, this is equivalent to you are dividing the noise by the channel itself. Okay, so typically, you have Y equals Hx plus noise. So for zero forcing, you just divide the received signal by H, right? So you divide here by H, you divide by the channel matrix. Okay, so this will give you
Fading channel.
H minus 1, which
No,
this one will cancel
H
this one.
is
Okay, but
H
here,
is
if I have a smaller coefficient here for, H, right? In this case, I will improve or enhance the noise because this is a noise. Okay, so this type of equalizer, linear or zero forcing equalizer, suffers from enhancing the noise. One of the solutions to do this is minimum mean square error. So for minimum mean square error, I do the same thing. I do the inverse, the pseudo inverse, which is, this is the simplest form of pseudo inverse, which this case, if I have a square H, okay? But if I have rectangular H, I go with this pseudo inverse. Okay, so here, what was the problem here? The problem here is this received vector or this channel itself, the coefficient might be small, right? And in this case, if you divide by small values, like 0.2 or whatever, then the noise will be improved, right? And I need to reduce this one, right? Not improving this one. Okay, so one of the ideas is the minimum mean square error in order to make sure that there is a proof actually for it. But in order to make sure that this is greater than 1, right? You add here the variance multiplied by identity matrix, okay, which is 1. So in this case, you make sure that this denominator, like always, like above 1, okay? So I add sigma square I. Okay, so for mean square error, it's a type of linear equalizer, follows the same equation as zero forcing. However, here we are trying to reduce the effect of noise enhancement as we have here in zero forcing, okay, by adding the noise variance multiplied by identity matrix. If you put the noise variance 0, you will obtain the same equation as zero forcing, okay? Both of them are linear equalizers. Okay, so example here, suppose that I have this H, this is a matrix, and I have the received signal here, and I have the noise variance. As you can see, it's like try to find the equalized symbols using a zero forcing and minimum mean square error. You just follow the rule, right? So like you prepare, as you can see here, I need actually H Hermitian times H, and then both of them are inverse, and then multiplied by H Hermitian. H Hermitian means that you rotate, and if you have a complex number, you make a conjugate, okay? But I will not include, if I decided to include this in the exam, I will not include the complex numbers. But anyhow, so you prepare H Hermitian H, you multiply, and then you obtain the inverse, and then you can find the weight by applying like just matrix multiplication. You find the weights of zero forcing, and then you take this weights of zero forcing and multiply it by received signal. The result will be the estimated symbol using a zero forcing. X estimated, right? Using a zero forcing. If you need actually to find minimum mean square error, you prepare the rule. So like you find like H transpose plus sigma square, right? So sigma square is 0.5 multiplied by identity matrix, and then you obtain this value, and then you can obtain the weights, the weighted matrix of minimum mean square error, and then you multiply it by y, the received signal, and then you obtain the x of the minimum mean square error. Okay, the last thing we will be explaining, I think we can discuss maximum likelihood next lecture. Okay, so anyhow, guys, I think as a coming lecture will be the last one, right? So we're supposed to discuss what will be included in the final exam. Okay, so because I think for undergrad is 28, right? So next Wednesday, Tuesday will be 29th, right? So it will be out of 28, okay? So or after 28. So the coming Friday or Wednesday, yes. Friday, we are Wednesday. Okay, so for Friday will be the last lecture. We'll be discussing in the last few minutes. We'll be discussing what will be included in the final exam, similar to what we did in the midterm exam. Okay?
Okay.
Yeah. Okay. Any question?